Good morning all. So today we will be discussing about the hyperspectral remote sensing for the mineral exploration. I am Richa and I am working as a scientist in Geosciences Department of IIRS. So as we all know that mineral exploration is a very tedious task if we do it normally or in the traditional way, because to understand all these mineralogy, weathering characteristics and all, it takes a lot of time and it is at times very tiresome also and time consuming. So for easing that or to take the advantage of remote sensing for the mineral exploration, what we can do, we can use with the limited human observation. This remote sensing technology, especially hyperspectral remote sensing, plays an important role in the mineral exploration. So let's see some example in multispectral, like maybe the Astra data, because the Astra data has got number of bands and its coverage all over the world is available. And then we will go for the next hyperspectral data sets such as Hyperion or Prisma or Everest. So this because remote sensing data, the advantages of the remote sensing data is its synoptic view and multispectral, hyperspectral and multi-temporal coverages also at time. So it can help us to delineate the different metallogenic provinces, belt sites and mineral guides over the terrain very easily. Now let's see that to explore anything, there are different exploration programs. It is in the prospecting stage or the regional exploration stage, detailed exploration stage or mine according to the GSI and mining departments. These are the different stages. So when we are talking about remote sensing, the initial prospecting and regional exploration stage, we can help a lot using the remote sensing data of different resolutions. So what are the things we are exactly depending upon? So the general geological setting, what are the different alteration zones, and the associated rocks and structures, lineaments, the oxidation products, morphology, drainage and vegetation anomaly, etc. So all these things, all these features we can interpret using the multispectral data and can be delineate more accurately. Compositional wise, identification of the material is possible using the hyperspectral data. So what are the different geological criteria? So we have to see, if we are searching for any mineral prospecting or mineral exploration, we have to go for all these stratigraphical or different types of guides, maybe stratigraphical lithological guides, geomorphological guides, structural guides, or we can look for some alterations and the geobotanical guides. So let's see all these things one by one, and how can remote sensing help in that. So these for the guide of lithology, if we are searching for with the help of remote sensing, the lithology and geomorphology, even with the help of multispectral, can be seen very nicely and can be, we can go for it. Now next, say the geobotanical guide. So when we are talking about hyperspectral remote sensing, I hope you all know a little bit about the hyperspectral, because in the multispectral we have got few bands, but in hyperspectral the number of bands are in hundreds. So with the help of that we can identify the material. Now as we say that geobotanical guide, so when there are certain mineralization present, because of that mineralization, the soil is also rich in a certain mineral, and that vegetation or the plant species or the fauna over there, they also floras over there, they will also have a unique condition. They are basically the toxic because of the presence of some minerals. So the leaf concentration of trace metals may indicate the composition of the underlying soil, and thus we can these can be very much helpful in the mineral exploration. So if we are talking about the leaf health, leaf concentration and all these things, these can be the spectra of different types of leaf can be identified using the hyperspectral data, and on the basis of that we can say that what are the compositional change in that concentration of the trace metals and etc can be identifiable, and we can say that the soil is rich in certain mineral, and as accordingly the exploration can be done. Now there are different guides, as I have told you. So first we have discussed about the geobotanical, second we are thinking about the lithological guides. So in that we can clearly see different types of lithology, or the what to say, different types of rock types present in the area. Sometimes the minerals are uh, bound with the lithology or certain rock type. Sometimes it is bound with certain structure and so on. So with the help of remote sensing, if I can clearly discriminate the lithologies, or I can clearly discriminate between the different rock types, then easily I can identify them. So, same with the geomorphology, like different morphological forms govern the prospection of the mineral deposits, which are the products of certain types of weathering and erosion. For example, fluvial deposits. So, if we can delineate them, we can identify the residual enrichment, like some monzite or some special areas also can be found at the fluvial. Then structures, there are different structures. Some kind of metallurgic provinces, they are orogenic belts or platforms, they are dependent distribution of there is there, or some ore bearing regions and fields within the metallurgic provinces are there. Then there are some localization of ore deposits in a particular ore field, and all this remote sensing is very much useful because the minor structural features in ore deposits can be seen very nicely. We can delineate the faulted bodies, so that if some mineral or ore deposits it's going along that and it is displaced by the fault, so we do not have to go linearly according to the displacement, we have to search for the further. Then your groundwater, oil, and your hydrocarbons, if we can see some folds or domal structures and all, they can be identified easily. Just for an example, the Khetri copper belt, India, it is also localized in the contact between the Alwar and the Ajabgarh group. So, if with the help of remote sensing, I am able to identify the difference between the Alwar and Ajabgarh, I can delineate that boundary, and along that boundary only the exploration can be done. Then there are different types of rock alterations can be seen, and those of rock alterations also serve as a guide for the mineralization. So different hydrothermal deposits such as base metals, copper, lead, zinc, etc., they show some significance in the alteration shows the significance in the hydrothermal deposits for the base metals. Now there are different types, maybe prophyllic, phyllic, opalic, quartz and limonite groups. They can have marked in the different zones or the rings of alteration. So if you see over here, these are the different rings of alteration. So if you see at the center, it's the red color portion, it's the Gosan. So maybe the weathered or the lemonitic zone. Then the dotted one is your, this dotted one is your ore zone. So just above the ore zone, you will see the Gosan and all. But mind it, it's not always necessary the presence of Gosan that the mineralization economically viable is present, because at times when Gosan is present but the enrichment of a certain mineral is not possible, so we won't be getting the economically important mineralized zone. But yes, nearby area Gosan may or may not indicate the areas. Then we have got potassic zone. So in that potassic there are some certain type of minerals as sericite, biotite, potassium. So when we are doing with the remote sensing data, especially with the hyperspectral remote sensing, if I am identifying the spectra one by one away from some particular center or in some regions, and I am able to getting the spectra or the minerals such as like this sericite, biotite, and potassium feldspar, I can say that this belongs to the zone which is the potassic alteration zone. If I am able to identify the mineral of quartz and pyrite and all, I will say that it is in phyllic zone. If I can see this clay minerals, kaolinite and montmorillonite, this is argillic zone. If I can identify calcite chloride, it is in prophyllic, like that. So this is what from center to away, from central to away direction, in all the direction away from the center, what we are getting the zones are getting changed gradually, and different zones have different characteristic minerals, and those characteristic minerals can be identified using the hyperspectral data. These are certain ratios that with the help of multispectral also we can be identified, like iron oxide, TM. This is for the TM, Lancet TM data set. So don't just go blindly by the bend number 3 by 1. the wavelength, equivalent wavelength of another satellite, maybe Aster or maybe OLI or so, has to be searched and then ratio to be made. Clay minerals 5 by 7, ferrous and all these like this. These are the different ratios. Now, this is just an example of the Aster data. We have performed the analysis of Aster data in Umra area. The data we have taken for 2003 of Aster area, Umra area, Rajasthan. And we have found different, we have done the ratioing and we found that the different minerals present over there or the open cast mines were highlighted very nicely and clearly using the ratio. Now, let's see the importance of hyperspectral. So, fault fractures we can identify using the multispectral. Hydrothermal altered rock at times can also be identified with that. But when we are talking about the mineral abundance or identification of material or identification of mineral, that is mainly possible using the hyperspectral imaging, using their spectral property of the pixel. Now, what is the spectra? It is just the when we insert a photon on a certain material, some things absorb, some transmitted, and some of that get reflected. So we study the reflected one, and we, for each and every mineral or material, the reflectance property or the reflectance spectra is very unique, and on the basis of that reflectance spectra, the absorption dips are unique, and those absorption dips are characteristics of the mineral composition as well as their crystal lattice structure. So, just the definition of some very renowned person in the field of this hyperspectral ones, and the Hunt and Sulbury, which has studied a lot on the reflectance properties of the minerals. So, the reflectance properties of the rock forming minerals are the function of the chemical composition and crystal structures, as I already discussed, such that many minerals have diagnostic absorption features in the electromagnetic spectrum. So, what I want to say is, when we are studying the reflectance spectroscopy, when we are studying the spectra, the absorption at a certain wavelength is more important or characteristic for the identification of the material instead of the reflectance. So, we have to concentrate more on absorption dips, not on the peaks, the dips at a certain wavelength for certain mineral. Just for the example, if you see different hydroxyl bearing minerals, we will have the spectral properties in between these ranges. For example, the presence of carbonates, we will have an absorption dip at 2.3. If the hydroxyl or HOH is present, then at 2.2 also we will get something. If it is because of the presence of HOH, it is at 1.4 and 1.9 also. So, these are the example. You see, this is for the mineral, iron minerals like goethite and hematite. If you see them clearly, we have got an absorption spectra at the absorption dip at around 0.9 to 1. The transition metals generally, these absorption dips we are getting it around 1 in the VNIR region. The spectrum is broad, okay. But when we are talking about the different spectra in higher SWIR region, the spectra, the dips are sharp and very peculiar. Peculiar dips are for this iron also, but iron dip is very broad. It will cover a few 2, 0.2, 0.3, like 0.8 to 1 micrometer range. Whereas when we are talking about these spectra of CO3 or H2O or all, it is very pinpointedly very sharp spectra absorption dip at certain wavelength, like H2O ke liye we will be getting it at 1.4 and 1.9 and 2.8 also. So for that presence of adsorbed water at Chandrayaan, this 2.8 absorption is this 2.8 absorption was important. Then we will get some around 2.2 for the ALOH and MgOH also. For CO3 it is at 2.3. So like that we have got different spectra at different wavelength, and those are important for the identification of that particular mineral composition. Now these are the different spectra for the iron oxides, clay and carbonates. If you see clearly here, this is for the hematite. So the spectra, broad spectra over here. Okay. Now at 1.4, because of the presence of water, 1.9 shows the presence of water. Here also at 2.2, the clays have spectra, the absorption dip at 2.2. This is MgOH, LOH, and this is there. Then the calcite will have the spectra at 2.3. So like that, different spectra, more or less the reflectance is similar, but the absorptions for different material, different chemical composition is different at different wavelength. Now this is for another rock forming minerals like for olivine, pyroxene, feldspar and all. They have got their spectra at different wavelengths, just for the information. Feldspar it is 1.1 to 1.3, carbonate 2.2 to 2.4, olivine 1 and 0.65, pyroxene 0.9, 1.05 and etc. like that. So we'll get these absorption dip, and these can be seen very clearly in the hyperspectral image spectra. Now let's see that these are the different spectra. Now when we are talking in practical, the every time each pixel is not pure. It may have the mixture of one or two minerals. So if you see over here, this absorption dip says that the around 0.9 to 1, that the iron is present. Okay, here it is the characteristics of goethite, FeOH, but after that there should be nothing, it should be straight. But in our spectra, the red one is the spectra we have collected in the lab, and white one is the spectra from the USGS library. These are for the pure minerals. Now there are certain differences in the pure and the spectra. We have collected samples in the field. Now you see that it has got the additional absorptions at 1.4, 1.9 and a doubly dip at 2.2. It means the spectrum what we have collected, or the surface whose spectrum has been collected, is the mixture of two. One is iron and the another one is kaolinite, because the absorption at 2.2, the double dip at 2.2 is the characteristic of the kaolinite. So if you see carefully this one, the third one, just follow my cursor. The absorption at 0.9 or 1 says the presence of iron. Absorption as 1.4, 1.9 shows the presence of hydroxyl, and at this 2.2. So all these 1.4, 1.9 and 2.2 says that some clay is present, because for kaolinite and all OH is there, no? So because of the presence of that OH, it is there. So this says that the spectra, this spectra is the mixture of two, goethite as well as kaolinite. So like that, different spectra can be identified, and those can be seen clearly. Okay, now let's see that. So the hyperspectral says the acquisition of images in hundreds of contiguous registered spectral bands, such that with the help of each pixel I can generate the whole spectrum. See, when we are generating with the multispectral, there are gaps in between. We are getting 9, 10, 12 points. So the spectra is not contiguous. It is crisscross, sharp. But when we are talking about hyperspectral, the spectra is very smooth. So because of that smoothness, each and every part is covered, because the spectral interval is very narrow. So we are getting lot of point, and because of the presence of lot of point, lot of bands, the bandwidth is in nanometers, the contiguous spectrum is possible. And because we are considering more about the absorption dip, so if we will be leaving some region, then some spectral absorption dips will be missing. So in the hyperspectral, when we start from a certain point, for example 0.4 micrometer, we will be continuously taking the data, the information from 0.4 to 2.5 or 1 or 3, whatever the sensor is designed up to. But there will be no gap. The spectrum, the capturing is contiguous, so that we can get a fine confined contiguous spectrum, so that we can identify the material. Now these are some case studies on the basis of that. This is for the Hyperion data. We have identified different minerals using this data, and we found that this this is for the argillaceous area. Argillaceous rocks are present, and the zone of hydrothermal alteration has been identified using the image data. Then hyperspectral image. This is for the Hyperion. Then we went to the field. We corroborate our results with the field studies and the lab studies, and finally publish the paper. Then this is the another area for the Purbanera and the Rampura Agucha area. This Rampura Agucha is very well open mine for lead and zinc. If you see this in the northeast corner, you can see this circle or the covered area. This is the open cast mine for lead and zinc. Now what we have found during the image analysis, that surrounding to this open pit where they have done this dumping and their dumping sites and pond and all, dumping pond, we are getting very clear signatures of pyrrhotite. So why we were thinking that pyrrhotite is there? Then we found that the pyrrhotite is associated with the sphalerite, galena, pyrite and all these as and different sulfide mineral as a secondary product. So in the dump, this pyrophyllite is present, and because of that the pyrophyllite is getting highlighted over here in this image. Now there are studies by some other authors also in using the Hyperion data set. You can see over here, this is the study from the Kusuma and all using the Hyperion. What have they done? They have tried to discriminate between the different types of bauxite, like bauxites, aluminous laterite and laterite, for the mineral exploration purpose only. So with the help of this, they are clearly able to differentiate between the three types: bauxite, laterite, also two types, the alumina rich and the normal laterite. So on that basis, they have classified it into the three classes, the lower one. And they have also done the XRD and XRF geochemical analysis to prove that their analysis using the spectra is right. And they found that the spectroscopy result is match very well with the mineralogy estimated by the XRD and XRF. Thus, the spectroscopy can be used, or the hyperspectral imaging can be used for the conventional exploration procedures for bauxite specifically. Now, another study by Cruz et al. In 1999, what have they done? They have tried different hyperspectral imagers and generated the spectrum. So, you see that with different spectrum, line profiler, there was a line profiler in 1982, and the IIRS system, this one is the IIRS one. The spectrum can be seen clearly from left to right. This is for the line profiler, this is for AIS, and this is for the IIRS. Now this IIRS they have developed in 1985 or 1990s only, and they are upgrading it. So recent data what we are getting is IIRS NG. So IIRS is new generation IIRS data we are getting. Now what they have found, that the distribution of these carbonates they have worked, and multiple sericite muscovite end members and also their distribution. So they have found sericite, calcite, these two different minerals, and there are type in sericite 1, 2, 3 different types of sericite. So with the help of the hyperspectral spectra only, they were able to identify, map clearly the three different types of sericites. There is some variation in the mineralogy, and the carbonates, and carbonates may they can identify the dolomite and calcite clearly. So the hydrothermal system at this has many of the elements of porphyric, copper and system. However, no supergene enrichment at present. That's why, as I have told you, that at times surface you can see some gosans or something, but the enrichment in the surface should be there to extract it economically. So in this case study, they have found that in the Grapevine Mountains, Nevada, that there are indications on the surface gosan present is there, and some but the supergene enrichment which is responsible for the deposition of these minerals, copper etc., is not present. Therefore, the copper whatever was there in very less amount, they were leached and weathered, and some surface signatures was present on the surface, but the economically important zone, or what to say, the mineralized zone for copper is not present in this area. Okay, then the another studies by Cruz, what have they done? They have seen the different spectra of different materials for the clays basically. So what have they said? They identify the minerals iron, hematite, goethite, and different clays, kaolinite, dictite, alunite, and all these, some micas also. So what they found, they mapped these things with the help of hyperspectral um, remote sensing, and they cross-checked it in the field, and they have found a very good correlation between that. They have generated the spectra using the ASD spectroradiometers also in the field, and the results were shown good correspondence. This is another paper of us. So what we have done, we have tried the different mapping algorithm used for the hyperspectral data. This we have done for the IIRS in the Rajasthan area, southeastern Rajasthan. So we have tried different algorithms like SAM, SFF, MTMF, and FC, and this is the FCC of the area. So what have we found, that the SAM, the spectral angle mapper algorithm, which is used for the classification of the hyperspectral data, is not able to differentiate between different classes very clearly, and it is misclassifying the material into the settlement and other classes, land use land cover classes. The SFF also, up to some extent, it is improving, but still it is mixing with land use land cover classes. Whereas when we perform this analysis using MTMF, mixed tune match filtering analysis, it says it is very well classifying the minerals or the geological classes. It is very much discriminating between the geology and land use land cover, and the results were quite good, with somehow more than 85 to 90%. Now this is another study using the IIRS NG in the Umra area, Rajasthan. So what have we done when the IIRS was flowing on our we have got the IIRS data, and that sensor flew in this area. We went to the field and we have taken some in situ observations in correspondence with the IIRS flight. So this is the open cast mine. We took few observations from this open cast mine, again in the northeast part, and we have collected the samples also, few spectra from this mine, and we came back. So after 6 months, when we got the data, the process, the georectified and radiometrically corrected data after 3-4 months or so, then we tried to do the classification using the image. So what we have found, that the spectra what we have collected, we matched with the open cast mine, they were very well matching. Then we tried to generate the, when we tried to classification the whole scene, and we found that there are some other places also the similar class is occurring. Then what we wanted to say, that we wanted to check that what exactly that these classes are, what are. So we went to the field, we verified, and with that local geologist also, we found that these all area which are classified in the image as the rock phosphate deposits are also, we have found that there are some places queries are there, so they have queried for rock phosphate, but their percentage is comparatively low. Economically, it's comparatively low, so it is not economically viable, and we were not able to do the extraction right now, but maybe in the later stage it can be done. So from known to unknown approach we have used. These are the known rock phosphate area. We have collected the spectra from here. We have matched with the IIRS the data, and then we have run the classification algorithm for the larger areas, and we found some new areas which were already not been highlighted by the agencies, or which is maybe queried for that, and they have got the similar composition of the area which we have done. So we can do the classification of the area. Some from known spectra we can generate either from the spectroradiometer or from the image, and then we can run the classification, or we can do the identification of the similar material in the overall area. Now, this is another example for the IIRS. This is near the Jamarkotra mine, the rock phosphate mine present in the Rajasthan. And what we see that when we have generated the spectra from the field as well as the spectra from the image itself, we have matched them, and we found that the area where we can find the dolomite, it is very well classified as the dolomite in the rock phosphate, because the dolomite is the host rock for the rock phosphate mineralization. Then at some places, because of the chlorite is there, the alteration also present can be seen. Now another example, this is the marble mine in the area. In that we can see that open cast mine, and this is very well characterized and identified by the image, in the image using the spectral matching algorithm. Now this is the very recent published studies of a study of us. What we have found that in the Banswara area of Rajasthan, there are different types of limestone present. So we try to see the like variation in the limestone. So there are two types of limestone present in that area, type 1 and type 2, that we can discriminate easily. And we found that the type 1 is the pure, comparatively pure limestone. The lime percent is 48 or approximately 49%, whereas the type 2, the limestone is, the lime percent is around, CO percent is around 44%. Now how did we discriminate between these two? We have done this using this absorption, what we can see at, because of the presence of MgOOH at 2.2. What we have found that the absorption at limestone type 2, Al2 and Mg, the limestone type 2 absorption is more for limestone type 2, whereas it is less in type 1. And if you see the geochemical result also, the percentage of Al2O3 in type 1 is around 0.5, whereas it is in type 2 1.1. It is almost double. Now if you measure the dip over here in between, then we have found that the depth of type 1 is 0.09, whereas for type 2 is 0.18. What I want to say is the compositionally variation is corresponding with the absorption dip present in that area. So more Al2 percentage, the more is the impurity in the form of lime. So in this way we can say that the limestone type 1 is pure, calcium is more and Al is less, whereas limestone type 2, Al2O3 is more, percentage is more, so the lime percentage is also less and it is comparatively impure. So these are the different studies what we have seen, and so we can say that with the help of the advances in the hyperspectral remote sensing and remote sensing advantages can be taken care for the mineral exploration, and this can be done very nicely, thoroughly, but with field observation. No doubt with the help of remote sensing we have constrained the field observations, or the field observations have been limited, but it is necessary and very very important to do the field verification, and field observation should be taken in the field. Samples should be collected and can be done. Now let's see, we have certain in our institute, because the observations what we can taken should be matched with the field observations, and how do we match the spectra observed from the remote sensing in the field. So to cater that, we have established a hyperspectral lab at our institute, and this lab we have purchased these spectroradiometers. So there are two ASD field spectroradiometers. Those spectroradiometers can range from 0.35 to 2.5 micrometers, and one FTIR spectroradiometer which gives in the range from 2 to 60 micrometers. Okay, so these are the spectroradiometers we have got. So we have got total number of 3 spectroradiometers, and with the help of these spectroradiometers, the spectra of any sample, any material, any rock or mineral, anything can be collected between 0.35 to 16 micrometer range. So this one, the FTIR, we generate the emissivity spectra, whereas in the ASD we generate the reflectance spectra. Now let's see how do we do it. So this is we have taken a project and we have generated different types of spectrum using that. So these are the normal what to say, pro forma in which we generate the spectra. So at the sample, because we are collecting the samples in the field from the sample locations, what do? We collect the photographs, we write the photo number, landmark descriptions, for example, where it is. So it is connecting to the road and around 20 kilometers southeast to the Udaipur or wherever at this MDR 11. Okay, then we write the LULC details, like it is the open cast mine surrounded by good agriculture, etc. Then we write the geomorphology. It is a penny plain. Then stratigraphic, it belongs to what stratigraphic formation, maybe a Delbara group or any Debari or something. So it is for the Debara group. Then the lithology in the field, what it suggests, or the field geology suggests that it is a rock phosphate ore and it has got quartzite phyllite mixed with the quartzite. So like that we have seen, and then we say that the associate mineral deposition, so rock phosphate mineral deposition is there, and is it a mine or not? So yes, it is the open cast mine, and it is presently working. The name is Matun. Now the spectrum what we have collected in the field. See, we have got three things: sample detail in the field, spectrum detail, spectra collected in the field, and we bring the sample and collect the spectra in the lab. Okay, so like this we are generating the spectrum library for each and every sample. So we have collected in the field, it is in 2016 morning 10:50 at the rock phosphate ore was collected. This is just the ID for our reference what we have given, and the instrument what we have used is the ASD field spec 4. So like that different spectrum we have collected. Okay, like we have collected the ore spectra, we have collected the mine waste spectra, etc. Now these are the things what I wanted to show you, the details. Like this is the location. We will just give a plot on the Google map that okay, from this location I have collected the spectrum. Then this is the field photo from that location itself. I am standing on that location and I have clicked the photograph of the original photograph of that area. So this is the photograph. This is, you can see the open cast mine. Okay, then this is the field photo, the surface from where I have collected the spectra. So from of this surface I have pointed my gun, the instrument I have kept over here, and I have collected the spectra of this surface, and this is the spectrum I have got. Okay, now at around 1.9 and 1.4 we are getting this noise because of the presence of water, and water absorption bands are present, and because of that we are getting the noise at 1.4 and 1.9. So this is the weathered one, sorry, the ore, it has got some iron impurities also. So you can see the spectral dip of iron also present over here. Then this is the another field photo from here of this surface I have collected the spectra, and this is the spectrum. Now we have brought the sample from there to the lab. This is the lab photograph of those samples in the lab, and this is the spectra in the lab. Now mind it that there is no absorption dip or absorption dip of water, presence of atmosphere over here, because in this lab we are collecting the spectra in contact with the sample. Okay, in the field we are keeping the distance between the sample and the our spectrum collecting device. That's why it is because we are collecting in the sunlight. So the light source is our sun, and there is a distance in between. So the atmospheric interaction is there. Because of that the water absorption band is present, and because of that the noise at 1.4 and 1.9 is there. But when we are talking about in the field, in the lab spectrum, this lab spectrum has been collected using the contact probe. So we have kept the surface which spectra we want to collect with the instrument in contact. So, and the light source is it is in the instrument itself, that contact probe itself. So the atmospheric interaction is not there, and because of that you cannot see the noise at 1.4. So like that. But yes, now if there are changes over here, but you see that whatever the contact in new or no contact, the sunlight or artificial light, the absorption dip at around 1000 0.9 is also there in the field, and it is also very much present in the lab. Okay, so these are some another examples what we have collected. These are the rock samples, the field spectra, rock sample, rock spectra, field spectra, rock sample, rock spectra. Some variations can be seen over here. If you normalize or if you subset this noise, these again the spectral features will be highlighted, and those are same. Now we have got the another spectroradiometer with us, that is called the FTIR spectroradiometer, and that spectroradiometer we calculate the spectrum from 2 to 16 micrometer in the emissivity range. So this is the sample of one quartzite rock which has got the malachite stains in it. So this we can see. So we have generated the spectra in using ASD. This surface will give you the quartzite. This surface where the stains are there will give you the malachite spectra. So malachite spectra was collected. Then what have we done? We have done the spectrum of malachite of this surface has been collected using the FTIR also. Okay, the emissivity spectra. Then we have corroborated this result. We have just matched this result with the XRD analysis. So XRD shows the peaks of malachites over here clearly in this 5.6, 3.368 and 2.8, and these are the three um, peaks shows that malachite is present. This spectra shows the presence of malachite. This spectra shows the malachite presence, and the presence or the findings we got it from the spectral. We collaborated. We just confirmed with our geochemical result, and the results were confirmed, and we found that the malachite is there. So like that, as with these several studies, we have proved that the spectral analysis, what we are getting, the same results we are getting with the geochemistry. So now we can also say that it is already proven in the theory that the spectra has unique and the unique spectral characteristics can be seen. So with the help of this, we can say that the spectra of each and every mineral, if you collect, and the spectra is unique, and you are able to find that uniqueness in the spectra, that this absorption dip is unique for that, then those absorption dips can be identified in the other areas, unknown areas, and the mineral exploration can be done with less difficulties, with less time, and quickly. So that's it. This is the dolomite exposures what we have collected in the field, and you can see that here we are collecting the spectrum. This is the instrument, this is the gun, and this is the data logger. With the help of this data logger, we are generating the spectra of this surface. So that's it from me, and these are some other photographs. Thank you.